Study Film, a production of the Chemical Education Materials Study. By this time in your study of chemistry, you are well aware of the fact that there are only about 100 elements. From these 100 elements, it is possible to prepare literally millions of compounds. On this table, we see representative compounds arranged according to their periodic properties. The compounds on the left end of the periodic table tend to be colorless. In this central region, most are colored. On the right side of the periodic table, most are colorless. You will recall in our arrangement of the elements that those to the far left are typically metallic, as characterized by relatively small gaseous ionization potentials, whereas these elements on the far right are typically non-metallic and have much higher gaseous ionization potentials. The elements in the middle are intermediate in both these properties. In column 1, the elements have achieved a single oxidation state, 1+. Those in column 2, 2+. By contrast, those in the central region have several oxidation states. Typical chromium states are +3 and +6. Manganese, 2, 4, and 7. So, we conclude that elements in this central region are intermediate in metallic nature and oxidation behavior, and that their compounds are generally colored. The elements in the central portion of this form of the periodic table have historically been known as transition elements. The transition elements share many properties in common, so that what we say of one would certainly be descriptive of the others. We shall focus our attention on but one of these transition elements, vanadium. Here is a sample of metallic vanadium. Notice its luster. Let us first investigate the oxidation states of vanadium. Like most metals, vanadium reacts with many oxidizing agents. Nitric acid is an especially strong one. The nitric acid is heated on this plate to increase the rate of reaction. The metal reacts with the nitric acid and dissolves. The presence of brownish nitrogen dioxide fumes shows that nitric acid has been reduced and the vanadium oxidized. When the reaction is complete, the solution contains vanadium in its highest oxidation state. Other experiments show that this vanadium is in the 5+ oxidation state. Here is a standard solution of 5+ vanadium. Let's try to reduce it to other oxidation states. Zinc is a good reducing agent. The zinc in this flask has been shaken with a small amount of mercury to form an amalgam. A color change occurs in the vanadium solution as soon as it contacts the amalgam. The amalgam provides a large clean surface for the reaction and minimizes the evolution of hydrogen gas. Shaking the flask increases the area of contact between the zinc and the vanadium solution. The solution turns blue. Let's continue the shaking. After several minutes with further shaking, the solution becomes a deep green. Now the green color disappears. Finally, a violet solution forms which undergoes no further reaction. What really has happened? Was the vanadium reduced? If so, to what oxidation state? Let's transfer 50 milliliters of the vanadium standard solution to a graduated cylinder with an accuracy of half of a milliliter. The solution that we're transferring then will contain 5/1000ths of 1 mole of vanadium in the positive 5 oxidation state. The solution is poured into the top of a glass column packed with zinc amalgam. Opening this stopcock partially evacuates the flask. Thus, when this stopcock is opened, the solution flows rapidly down the column and comes into intimate contact with the zinc amalgam. This operation is equivalent to many minutes of shaking in a flask. Just as before, the vanadium changes to the violet form. The apparatus is washed through with the distilled water to be sure that all of the 5/1000ths mole of vanadium is removed. To test the oxidation state of our sample, we'll add a powerful oxidizing agent, the ceric or cerium-4 ion. The Roman numeral indicates its oxidation state. When yellowish cerium-4 acts as an oxidizing agent, it gains 1 electron per ion and becomes colorless cerium-3. Thus, each mole of cerium-4 ion will gain 1 mole of electrons. Now to our 5/1000ths mole of vanadium, we add 5/1000ths mole of cerium. The same green vanadium is formed as in the shaking experiments. Oxidation of the vanadium has occurred. Since each mole of cerium ion has gained a mole of electrons, each mole of violet vanadium has formed a mole of green vanadium by yielding a mole of electrons. If we call the unknown oxidation state of violet vanadium N, that of green vanadium must be N+1. They differ by 1 electron per atom, or 1 oxidation number. Let's try to oxidize the vanadium further by adding another 5/1000ths mole of cerium-4 ion. The vanadium is now oxidized to the blue form. Here, each mole of green vanadium gives a mole of blue vanadium and a mole of electrons. Blue vanadium must be 1 oxidation number higher than green vanadium. Let's add another 5/1000ths mole of cerium-4 ion. We get the original yellow vanadium species, the vanadate. The vanadium in yellow vanadate must be 1 oxidation number higher than blue vanadium. Further addition of cerium-4 ion produces no change. This experiment confirms that the vanadium in the yellow vanadate is in its highest oxidation state. Here are samples of vanadium in each oxidation state.
We do not know the formulas of the colored ions, so again we use Roman numerals to indicate the oxidation states. We know the yellow species is +5. So the blue, which is one oxidation state lower, must be 4. The green, 3, and the violet, 2. Now let's see if we can associate the vanadium oxidation states we have observed with the possible electron structures.
The element vanadium in the free state has 23 electrons. These electrons are distributed 2 in the 1s, a total of 8 in the second, a total of 8 in the 3s and 3p, 2 electrons in the 4s, and 3 electrons individually distributed in the 3d orbitals. Let's examine the changes in electron configuration that would occur as vanadium participates in the various reactions. Or perhaps you would prefer to stop the projector and work out these changes in configuration yourself. The lowest oxidation state for vanadium as it participates in compound formation is 2+. This would correspond to the loss of the 2 4s electrons, leaving 3 half-filled orbitals. They could be lost one at a time, giving vanadium in the 3+ state, 4+ state, and 5+ state, respectively. The other electrons are too tightly held to participate in compound formation. This agrees with the experimental fact that yellow vanadate solution represents vanadium in its highest oxidation state, 5+. In a similar fashion, the chemistry of other transition metals is better understood by examining the partially filled 3d, 4d, 5d orbitals. In fact, the explanation for color is found by a closer examination of the 3d energy states.
A more detailed picture shows a small energy separation. This separation matches the energy of certain visible light photons. When the orbitals are partially filled, absorption of a photon moves an electron to an empty orbital. The transmitted light will then be colored. Thus, the color of vanadium-2 is due to light absorption by its 3d electrons. The vanadium-3 and vanadium-4 also have d electrons and are also deeply colored. Conversely, the lighter color of vanadium-5 is consistent with an absence of 3d electrons. In a like manner, most compounds of transition elements are deeply colored because of partially filled d orbitals.
Now let's investigate some of the chemical properties of vanadium in its several oxidation states.
We place some green vanadium-3 solution on a magnetic stirrer. Sodium hydroxide is added to the vanadium solution. The precipitate that is forming is the hydroxide of vanadium-3. The magnetic stirrer disperses this as fine particles of suspended material and gives a muddy appearance to the mixture. But what is happening on the molecular level? At the start of the experiment, the vanadium-3 ion is strongly bonded to water molecules, 4 of which are schematically shown here in 2 dimensions. The positive vanadium repels the hydrogens. The added hydroxide ions remove hydrogen ions from the water molecules, leaving hydroxides bonded to the vanadium. This combination of negative hydroxide and positive vanadium lowers the positive charge of the aggregate. The precipitate forms when the aggregate becomes electrically neutral. Let's add more sodium hydroxide. No reaction is visible. the neutral precipitate does not dissolve. It remains inert toward additional hydroxide ions.
Now let's see what happens when we add the sodium hydroxide to the vanadium 4.
Again, a precipitate forms. Once more, we add more hydroxide. Unlike the vanadium 3, the precipitate dissolves, leaving a brownish solution. This phenomenon is better seen when a thin layer of the final vanadium 3 suspension is compared to a thin layer of the final vanadium 4 solution. Why does the vanadium 4 precipitate dissolve in an excess of sodium hydroxide when the vanadium 3 precipitate does not dissolve in an excess of this base? When a vanadium atom loses 2 electrons, the resulting ion has a charge of 2+. The ion is smaller than the atom because the remaining electrons are attracted more strongly by the nucleus. The loss of additional electrons results in a series of ions with an increase in positive charge and a decrease in volume. This difference in charge and volume accounts in part for the difference in behavior between vanadium 3 and vanadium 4. In water, both vanadium ions form stable metal-oxygen bonds. However, since the vanadium 4 is a smaller and more highly charged ion, and it repels the hydrogen ion even more strongly than does the vanadium 3. In fact, with vanadium 4, even water molecules can remove these protons. This leaves the oxo ion VO2+. The VO2+ remains in solution bonded to other water molecules. As hydroxide ions are added, they remove additional protons and form electrically neutral aggregates. The neutral species precipitates, just as with vanadium 3. However, in contrast to vanadium 3, the hydrogen ions here are so strongly repelled that additional hydroxide can react, leaving negatively charged species which go into solution. Thus, the increased charge and decreased size of the vanadium 4 ion causes its hydroxide to dissolve in excess base. After the film, you might like to discuss how vanadium 2 and vanadium 5 would react with sodium hydroxide.
So far, we have only concerned ourselves with the chemistry of vanadium in the presence of water molecules and the hydroxide ion. Now let's study the chemistry of some of the vanadium ions in the presence of other negatively charged ions,
such as thiocyanate and sulfite. Here are samples of vanadium in its 4 oxidation states: vanadium 2, 3, 4, and 5. First, we'll add sodium thiocyanate solution to the bottom row. These color changes are indicative of the formation of complex ions. They contain thiocyanate and are more stable than the water complexes with which we started. Now let's add some sodium sulfite solution to the middle row. Still other species of complex ions are formed. But note the vanadium-4 and the vanadium-5 in each of the lower two rows are very similar. This similarity is because the vanadium-5 has been reduced to vanadium-4, followed by complexing in each case. The formation of complexes is characteristic of transition elements like vanadium.
We have studied some of the important chemical properties of the element vanadium.
The intense color of some of its compounds, the variable oxidation states in aqueous solutions, and the formation of complex ions. All of these properties may be interpreted in terms of partially filled d orbitals. Our study of the chemistry of vanadium should aid us in understanding the properties of the remaining 29 transition elements.